Hello everyone, my name is Aaron Martinez. It's a pleasure to participate in this year's conference of the CSEE. And on behalf of my colleagues, I'm going to present our work title, Discovery of Energy Performance Patterns for Residential Buildings through Machine Learning Techniques in New York City. Um, as a brief outline, I'm going to start with the introduction, followed by some previous related studies. Then the case study will be described, and the hybrid proposed methodology will be explained to finalize with some validation and discussion of the results and some conclusions and takeaway message. The identified problem that this study aims to tackle is the lack of energy efficient and sustainable buildings, with the main goal of discover and analyze and predict energy consumption and greenhouse gas performance patterns for residential buildings in New York City, with three major objectives. The first one is to find correlations and similarities among site EUI, greenhouse gas emission intensity, and the wide variation of building characteristics, location, and energy-related historical data. The second one is to identify and analyze the main energy and greenhouse gas performance patterns. And the third one is to predict quantitatively the greenhouse gas emission intensity and site EUI and energy efficiency. As part of the background and motivation, in signing the Paris Agreement, New York City has committed to prevent global average temperature from passing the threshold of 2 centigrade degrees above pre-industrial average, so as to avoid the most dangerous consequences of global warming. And the building sector in the US accounts for 40% of the total energy consumption, with an expected increase of 5% by 2040. And nearly 75% of New York City greenhouse gas emissions comes from the energy used in buildings. And the reason that we selected New York City for this study is that it is ranked as the second major city in the world based on the Global Power City Index published by the Institute of Urban Strategies, and New York City pursues the global goal included in the Plan New York City of reducing greenhouse gas emission by 80% by 2050. Some of the previous studies, several authors shown in the table have carried out similar studies by applying classification and regression machine learning techniques to predict building energy consumptions based on the most influential predictor or attributes such as building characteristics, building age, location, and weather historical data. Some of these authors are shown in the table, and they have reached the shown accuracies with ranges from 87% to 94%. And they have found important association between this parameter and the building energy consumption. As part of the case study description, we focused the study at the building scale for New York City residential buildings, and the raw data set was retrieved from New York City Open Portal, consisting of 85K data points and 60 attributes, among which are gross floor area, bureau, year bill, weather normalized site UI, etc. And the proposed hybrid methodology is composed of supervised learning and supervised and unsupervised learning. And it started with some data pre-processing by removing missing and inconsistent values, then some outlier removal by anomaly detection, then the application of unsupervised learning by association rule mining, which was a base for applying also the supervised learning through regression, and through classification. For classification, we apply two main algorithms, KNN and decision tree, and for regression, we apply mainly multilinear regression, because support vector regression was discarded because of not reaching the better accuracies that multilinear regression. And these results were validated by cross validation And finally, the accuracy was good, consistent accuracies were received or got. Then we validate our results through GIS validation, and we extracted the rules from the association rule mining and the rules from the decision tree, and then compare the most significant, and we extracted the most significant parameters based on these rules, and we documented our results. As part of the data preparation, as I mentioned, we did some feature selection, removing of missing values, outlier removal, and the clean data set resulted in 30.3K building data points and 23 attributes. The selected independent attributes include gross floor area, year build, weather normalized site UI, and GHGE, direct and indirect, and among others. And the three main dependent variables include energy efficiency grade, greenhouse gas emission intensity, and weather normalized site UI. One important step in our methodology was the discretization of the main target attributes based on a statistical quartile base, as shown on the table on the right, and we use RapidMiner Studio to develop our models and to apply our algorithms. The first algorithm that we applied on supervised learning is the affinity analysis, and consisted of three major steps: the selection of the required attributes, applying the frequent pattern growth algorithm with minimum support of 20%, and creating the association rules with minimum confidence of 20%. And here you can see on the right a process carried out in RapidMiner. Okay, the most relevant rules were extracted based on the defined threshold, and we were particularly interested in those rules with worse building performance as their conclusion. For instance, the second rule shown in the table: if the weather normalized site electricity is low and the year build of the building is between 94 and 58 years old, then the indirect greenhouse gas emission of the building is high and belonging to the Borough of Bronx. The second algorithm to be compared with affinity analysis rules, we apply decision tree classification as part of supervised learning with three major categories as predictor attributes: geographical, physical, and energy related, with the shown attributes. And we developed three models for three different target variables: weather site normalized, greenhouse gas emission intensity, and building efficiency. And you can see an example of the extracted tree here for greenhouse gas emission intensity. Here are the main results from applying decision tree. Similar to the rules defined from affinity analysis, we extracted the most significant rules for the buildings with worst performance, energy performance of the buildings. Besides, the table shows the accuracy reached by the developed models and their performance metrics. In parallel, we run key nearest neighbor classification, and we reach the accuracies of the developed models for weather site normalized at 91% and greenhouse gas emission for 88, sorry. And here are some visualization of our results. Finally, we run regression algorithm as part of supervised learning, and we run the multilinear regression for three different models with three different target attributes, which are the same: greenhouse gas emission intensity, site UI, and energy efficiency grade. We got very good results of the models, and as you can see on the bottom, the graphic results follow a normal distribution for the prediction models, which somehow validate our models. And we also extracted the attributes with high level of significance for the prediction of our models. As part of the validation and GIS validation and results and analysis, the highest proportion, we found out that the highest proportion of residential buildings with low energy efficiency grade belongs to Manhattan and Bronx Borough, the same as the highest volume of direct greenhouse gas emission released to the atmosphere. So special attention is required for Manhattan and Bronx boroughs. And the average, another important observation, it was that the average greenhouse gas emission intensity for the whole New York City residential building has not decreased in 4 years, emitting a minimum constant of 4.85 metric tons. And the number of buildings in the class of site high UI is higher than those in low and medium classes for the 5 boroughs. And one GIS validation at the building level for a specific building identification number and year built was compared versus the measured result GIS given by Mayor Office of Sustainability versus our predicted classification results and predicted multilinear regression results. As part of the conclusion, I would like to close this presentation with a reflection. The clock is ticking. What are we going to do to leave a better future to the next generation? What is the contribution of the construction industry to the world climate clock? If New York City keeps the same consumption patterns for upcoming years, then the city will not be able to reach the goal of reducing 80% of greenhouse gas emissions by 2050. Unless energy efficiency programs get implemented, including the incorporation of green energies and improvement of its energy distribution management system. And that is part of the contribution that we wanted with this study. Thank you very much for your attention and for your time.